How does lack of QKD standardization impact quantum cryptography? Imagine trying to build a puzzle with pieces from different sets. Without a common standard, fitting everything together becomes a challenge. That's similar to what happens in quantum cryptography when there are no agreed standards for quantum key distribution. Quantum key distribution is a way to share encryption keys securely using the principles of quantum physics. The idea is that any eavesdropper trying to listen in will disturb the quantum states, making it detectable. But in real life, the devices and systems used to implement QKD are complex and vary widely. Without standard rules, it's hard to tell if different systems will work well together or if they are truly secure. One major problem is security validation. Without standards, it's tough to prove that a QKD system can resist attacks in real-world conditions. For example, hardware like photon detectors might behave differently than expected, creating vulnerabilities. This means security claims can't be easily verified or trusted. Interoperability is another issue. QKD systems need to connect with existing optical communication networks. Without common protocols and interfaces, different devices might not communicate properly. This makes large-scale deployment difficult and slows down adoption. Measuring and testing quantum devices also becomes complicated. For example, how do you standardize the measurement of photon counts at telecom wavelengths? Without clear guidelines, certification is inconsistent, and it's hard to compare different systems. There are many types of QKD protocols, such as discrete variable, continuous variable, and entanglement-based methods. Without standards, each implementation might interpret these protocols differently, leading to confusion and difficulty in certifying systems. Security risks extend beyond eavesdropping. Attackers could disrupt communication without stealing information, known as denial-of-service attacks. Without operational standards, it's harder to develop effective countermeasures. Finally, for QKD to be used in critical areas like national security or banking, formal certification based on standards is essential. Without these, regulatory approval and commercial use are delayed. In essence, the absence of standardization creates hurdles for security, compatibility, and trust in quantum cryptography systems. Developing clear, international standards for protocols, device testing, and network integration is key to making quantum cryptography reliable and widely used. While efforts are underway globally, establishing these standards remains a major step needed to bring quantum communication into everyday life.